Hello everyone, my name is Akhlaq Ahmed. I'm an assistant professor at TED University, Turkey. I'm here to present our ICDE 2023 paper titled Accelerating K-Core Decomposition by a GPU. The work is done in collaboration with people from University of Alabama at Birmingham and Rowan University. I'll first introduce the problem, then I'll be talking about existing solution. I'll present our own solution, and finally experimental results will be discussed. K-core of a graph is defined as largest induced subgraph with minimum degree equals to k. For example, in this graph, entire of the graph is one core because every vertex have at least degree equals to 1. Two core of the graph is an induced subgraph where each vertex have at least degree 2. Yellow and red vertices are comprised of two core of the graph. Three core of the graph is shown in red where each vertex have at least degree 3. K-core decomposition is a problem to find core number of every vertex that is the largest value of k that v belongs to a k-core. All the green vertices shown in the graph have core number 1, yellow vertices have core number 2, and red vertices have core number 3. There are many applications of K-core decomposition, including community detection, detecting protein interactions, etc. Peeling algorithm is one of the methods to find K-core decomposition, where vertices with degree k are repeatedly removed from the graph with k equals to 1, 2, 3, and so on. Vertex degree is initialized as a core number, then it's updated as the vertices are removed from the graph. In this example graph, all the green vertices are degree 1 vertices, hence the core number of these vertices is 1. They are removed in first iteration, and the degrees of their neighbors are updated. The yellow vertices are degree 2 vertices, hence they are removed in the second step. Their core number is 2, and they are removed from the graph as well. As the vertices are removed, their neighbor's degree can also reach to k. Hence, they are also removed from the graph, as the core number of such vertices is also k. The yellow vertex here was previously degree 3 vertex, but now its degree is 2, hence it is removed. Finally, red vertices are removed from the graph with degree 3, as the core numbers of all vertices in the graph is calculated, so the algorithm stops. There are many solutions in the literature for K-core decomposition. The work of Bataglich and Zversky, hereafter abbreviated as BZ, implements a serial version of peeling algorithm in linear time complexity. Although their work is noteworthy, the serial implementation limits the performance. Hence, studies have been done to parallelize the algorithm. Parquet is the first parallel implementation of the peeling algorithm. Multi-core parallel system is used in this work. The algorithm have two phases, scan and loop, and the phases are repeated for k equals to 1, 2, 3, and so on. In the scan phase, vertices of degree k are collected in the buffer for further processing in the loop phase. For example, when k equals to 1, the vertices A, C, D, E, and F are collected, and they are placed in the buffer. Then loop phase is run, where each thread processes a vertex placed in the buffer. As the vertices A, C, D are processed, they are removed from the graph, and their neighbor's degree is reduced by 1. After the removal, vertex B is now at degree 1, hence it is appended to the new buffer. The new buffer, B new, is used to collect vertices during the loop phase. Now, E and F vertices are processed and removed from the graph. It caused G vertex to be added to the new buffer. Certain threads can sit idle as there are no more vertices in the buffer to process, hence wasting the resources. Once the buffer B gets empty, all the threads synchronize and new buffer is swapped with the buffer. Now vertices in B are processed. Now vertices B and G are processed and it caused buffers to be empty. The iteration stops when both the buffers are empty. Then the algorithm runs for next iteration, k equals to 2, 3, and so on, until all the vertices are removed from the graph. Further iterations are not shown here for brevity. PKC is an improvement to Parquet. It is still multi-core parallel implementation of peeling algorithm. However, the novelty of PKC is to use a thread local buffer to store vertices, rather than a single global buffer. Using the local buffer, there is no need for synchronization in the loop phase. In the scan phase, the thread examines vertices degree equals to k and append the vertices to their local buffers. In this example, vertices with degree equals to 1 are appended to the buffers. The vertices in the local buffers are examined by corresponding threads, and any new vertex is also appended to the local buffer. As vertex A is processed, vertex B is appended to the local thread buffer. Hence, there is no need for synchronization among the threads. A thread keeps processing until its buffer gets empty. An iteration completes. When buffers are empty, it then proceeds to next value of k. K-core decomposition have also been solved in distributed environment. MPM is a pioneer algorithm in this direction, which was later adapted by several other studies. In the MPM algorithm, each vertex performs an index style local updates to find core value of the vertex. In this graph, each vertex is assigned with its core value. Next, we illustrate how MPM finds this core value. Each vertex is initialized by its degree. Then each vertex calculates its support value based on the degrees of its neighbor. A vertex reads the core values of all its neighbors and sorts in descending order. As an example, consider the circled vertex. It reads all the neighbors' core values and sorts. It then calculates its support value as 3 because it has 3 neighbors of at least degree equals to 3. Hence, the core value of this vertex is updated to 3. The same is done by every vertex repeatedly until h-index operator converges. As a result, core number is calculated for all the vertices. There are only few studies for K-core decomposition on GPU. VETGA is state-of-the-art GPU-based implementation. It reframes the peeling algorithm to PyTorch vector primitives. It uses NumPy to load the graphs, which becomes too slow in loading, as well as the execution performance of the algorithm cannot get a native scale, especially for the large graphs. Our solution is a peeling algorithm adapted for GPU-friendly execution. It is implemented in CUDA C++ to achieve native performance. Our contributions are: we implemented peeling algorithm adapted specifically for a GPU. We implemented various optimization techniques on top of basic algorithm. We compared our results with 3 think like a vertex graph parallel systems, which are Medusa, Gunrock, and G Switch. We performed extensive experiment on 20 public datasets. To briefly explain GPU architecture, let's look at this figure, where a GPU device is connected to the host CPU. A kernel is a special program to be executed on device. From the hardware perspective, a GPU device consists of an array of streaming multiprocessors called SMs, where each SM has a set of execution unit and a chunk of shared memory. Thread block is an abstraction to SM, and CUDA schedules a thread block to an SM. Global memory is available to all of the blocks. In an NVIDIA GPU, the basic unit of execution is WOP. A WOP is a collection of 32 threads which execute single instruction multiple data. To achieve high performance, threads within a WOP should access consecutive memory locations called coalesced memory access. Our algorithm takes a graph as input and finds core value of every vertex. It applies peeling algorithm repeatedly for k equals to 0, 1, 2, and so on. A count variable is initialized to 0. It keeps track of how many vertices have been processed so far. At every iteration, it calls a scan kernel followed by a loop kernel. The loop kernel increments the count with number of vertices found at level k. Next, we explain both of the kernels. The scan kernel collects vertices with degree k. Each block maintains a local buffer to store vertices. All the threads in a block write the data to their block-specific buffer. Every thread of a block examines k degree vertices and appends them in the buffer. Assume that vertices A, F, C, G, X, O, and P have degree k. Thread block examine the vertices in a coalesced pattern, successively and repeatedly scanning entire of the vertex area until the vertices of degree k are collected. In the loop kernel, a WOP is deployed to process a vertex found in the buffer. Since there are 32 threads in a WOP, hence neighbors are processed in a batch of 32 each time. The neighbors are stored consecutively in the adjacency list, hence the SS is coalesced. Each thread checks the degree of a neighbor of V, denoted as U. If degree of U is greater than K, it decrements degree of U. If degree of U is equals to K, it appends U to local buffer of the block. However, this is still a naive version. It can cause problem due to parallel execution of the WOP. To illustrate a potential problem, consider this graph where all the vertices have core value of 2. When k equals to 2, vertices 1, 2, 3, and 4 are appended to the buffer and their neighbors examination is done in parallel. Thread A finds neighbors of vertex 1, that is vertex 0. It has degree higher than 2, so decrements its value. Thread B does the same, and now vertex 0 degree is 2. Thread C does the same, hence degree of vertex 0 becomes 1. Finally, thread D decrements and now vertex 0 degree becomes 0. However, correct value of vertex 0 should be 2, as it belongs to 2 core. To fix this issue, the threads will adjust the neighbor's degree by incrementing 1 if the neighbor's degree has fallen below the current level k. When thread A finishes, it checks the old value of it received for vertex 0 and compares it with k. That is the last condition of the code shown above. As the condition is failed, it does not increment. Thread B appends vertex 0 to the buffer for further processing. Thread B checks the last condition, however it fails. Thread C evaluates the last condition true, hence it increments degree of vertex 0. Thread D also evaluates the last condition to true, hence it increments the value. As a result, the vertex 0 have finally got correct core value, that is 2. Recall that we maintain a buffer at block level, hence all the threads within a block append vertices to the same buffer. Since this is done in parallel, so we need a mechanism to thread save. It can be achieved in two ways, by atomic operation and by compacting. By atomic operation, one vertex can be appended to the buffer at a time. Consider that E is pointing to current end of the buffer. We perform an atomic operation to find position of the vertex to be appended. The atomic operation returns a position that is safe to store the vertex. The endpoint of buffer is moved 1 point forward. Finally, V is appended on the position. The other method for buffer appending is compacting. Multiple vertices can be appended by a compact operation, where a scan is applied to find safe indices of the vertices. Assume that a warp has vertices A, B, C, D, and E to be appended. It first calculates a predicate array, which has one only for those locations that need to be appended. Then a scan is applied that returns indices of the buffer where vertices would be written. The buffer tail is added with the index of the last lane summed with its predicate value. Hence, the green region of the buffer is now safe to write 5 vertices. Finally, the vertices are appended by using the predicate and indices array. To perform warp level compacting, we can apply Hilly-Steele scan, shown on the left side. It iteratively sums up predicate values by jumping and adding 1 hop, 2 hop, 4 hop, and so on locations. Note that a warp is 32 threads long. Here, only 8 threads are shown for brevity. It takes logarithmic iterations to calculate the scan. Another method is to use warp void functions called valid scan. It is shown on the right side. The predicate values are packed and broadcasted to all the lanes. Then a mask is applied to find prefix sum of a particular lane. Finally, POPC function gives the prefix sum. All of these functions are hardware supported, and the scan is calculated only by 3 instructions. A block level compacting can be adopted in scan K phase. Here each warp is firstly scanned. Then a warp sum is collected to the first warp. Then Hilly-Steele scan is applied to the first warp. Finally, each warp scanned values are added with the results found in the first warp. As a result, a block level scan is calculated. We applied some optimization techniques on top of our basic algorithm. One of the techniques is to utilize shared memory in the loop phase. In the scan phase, the vertices are placed in a global buffer. However, when new vertices are found in the loop phase, they are firstly appended to shared memory until shared memory exhausts. Then we continue placing the vertices in global memory buffer. Another optimization technique is to prefetch the vertices in shared memory. For this purpose, warp 0 prefetches the vertices to be processed in the next iteration, while the rest of the warps are processing. The goal of this optimization technique is to reduce memory latency, as shared memory is faster as compared to global memory of the device. Then we implemented K-core decomposition on 3-graph parallel system. On Medusa, we implemented NPM style algorithm as a user-defined function. We also implemented peeling algorithm on Medusa, Gunrock, and G-Switch. We run our experiments on host with 2.4 GHz and 256 GB RAM. Our device is NVIDIA Tesla P100 GPU. It has 16 GB of global memory. We worked with 20 public graph datasets and repeated the GPU program 100 times and reported the averages. The selected datasets are of different size and categories. We tested pretty large graphs of up to 100 millions of vertices and billions of edges. We developed 3 versions of the algorithm differentiated by how the buffer appending is done. Our hours column is the execution time when atomic operations are done for buffer appending. BC is when valid compact is applied, and EC is when the efficient compact is applied by using Hilly-Steele scan. Please note that all the results are in milliseconds. We tried the optimization technique with all 3 versions. SM is the shared memory buffering, and VP is vertex prefetching. The hours version performed the best in all of the dataset, except in trackers datasets where it lags marginally. This behavior is observed due to the fact that atomic operations are highly optimized in GPU as of now. Therefore, the old school optimization techniques adds up their implementation overheads. We compared ours result with other GPU programs, and it can be seen that ours algorithm is several orders of magnitude faster than all other GPU-based solutions. Also, memory consumption of other solutions are much higher as compared to ours. In several datasets, other GPU programs fail due to out of memory or the execution time is more than 1 hour. In some datasets, even the loading time is more than 1 hour for Vetka, as it uses NumPy to load datasets. We also compared ours result with CPU programs, which includes Python-based network X library functions, Bize, serial and parallel version of Parquet, serial and parallel version of PKC, and NPM algorithm. It can be clearly seen that ours algorithm is fastest compared to all others, and there is several orders of magnitude difference in the performance. In conclusion, we developed highly efficient peeling algorithm on a GPU. It achieves native performance as it being a GPU-friendly algorithm. Currently, buffer capacity is a limit, although it works for pretty large datasets. However, if the buffer overflows for some very large datasets, our algorithm might fail. We plan to extend our work for multi-GPU environment where more memory would be available. We also found that atomic operations are highly optimized, and as of now, modern GPU programs should not rely on old school optimization technique, which often perform worse. Thank you for your attention. Please check out the links.